So to link up this topic with the previously studied topics that we covered, let's rewrite the dynamic model that were under consideration for us. For that means the dynamic model for the synchronous machine. So basically it was a third order model if we take only the synchronous machine. So, and of course in the linearized version it was in the incremental form, so it was del delta, and that was expressed as omega base del omega. Then we had the del omega, which was represented as del pm minus del pe. Of course, del p were further elaborated in terms of the k constants. The third state variable for the synchronous machine representation was this, that is eq dash, and the expression was like this. And again, of course, the del eq was further decomposed with the help of k3 and k4 constants. So this was the third order model we started with. Then we incorporated the exciter dynamics that was represented by the K over TA, the gain and the time constants for the automatic voltage regulator. And at the summing junction of the exciter block, we had these two signals available. And of course, later on, we introduced the UPSS. And then, so this was the exciter or the automatic voltage regulator block. And later on, depending on the stages of number of stages available in the UPSS or number of stages required in the UPSS, we had a few more state equations. So this is the summary that we have actually covered up till now. So from today onwards, we'll be slowly looking into the dynamic of this part. So if you remember in this model that I have written over here, we were actually considering two control inputs. One of the control inputs was del PM and the second control input was del VREF. This was coming, we are always saying that this would come from the mechanical side. So this would come from the turbine, air, and the governor combination. So this would come from there. And this would come from the exciter. Okay. So if you have some sort of control mechanism implemented, then we can have some value for del VREF and we can also have some values for del PM, which would be dynamic in nature. Okay. Condition is we have to implement some sort of control. Otherwise, they would be treated as some step change or some sort of disturbance variable. So to make them as a part of the control variable or to make them in the dynamic mode, to represent them in the dynamic mode, we have to take the dynamic model for the turbine and governor, specifically if we are interested in del PM. So basically what we are looking for is something like this, del PM dot or d del PM over dt. This is in the incremental form, and in the normal form or in the generalized variable form, that is in the non-linear form, you can say, this can be also written as dPm over dt. So in general, we are looking for the change in PM with respect to time, something like that. So this is our target for the first part of the lecture today, okay? And that would be achieved actually from the turbine modeling, the dynamic modeling of the turbine. So once we can do that, once we will complete this, we should be able to write down this state equation. And of course, the modeling size or the complexity of our power system model would increase slowly and slowly. So this is the target, and let's start looking into the hydro turbine model. So in the conventional power system, as we all know that mostly you have either the gas turbine or the steam turbine or the hydro turbine part. We will take one of those, okay, for our course. We are not going to discuss all of those, but the basic building mechanism is the same. Okay, we start from some basic physics or basic laws, and slowly we go into the dynamic part. Okay, for any sort of turbine modeling, be it the steam turbine or be it the hydro turbine or be it the gas turbine. Of course, the physics, the background physics would vary from one to the other. So let's start. So to start with, as we already know, actually, from the synchronous machine, let's say this is the stator part, or the part from where we will expect some output voltage or output power into the network. Let's say it is delivering. So these are the terminals. It is delivering some power PE and also some power QE at some terminal voltage VT. Okay, so these are the outcome. And this is the, let's say, the rotor part, where the rotor is actually excited by some DC voltage. So this is your VDC. And this part already we have covered. Okay, this VDC modeling part or the exciter part is already taken into consideration. So now what we will look into basically is this part. We'll be looking into the prime mover part. Okay, so that is our target. So what is the job of this prime mover? If you vary the speed of the prime mover, which of these parameters would be affected? If we vary the speed of the prime mover here, let's say this is the speed, omega of the prime mover. So if omega of the prime mover varies, it goes up or down, which one of these would be varied? Anyone?
Mechanical power.
Sorry?
Mechanical power.
Mechanical power. Okay. Okay, so mechanical power. So I haven't written it here. So mechanical power. Okay. Actually, if you vary the mechanical power input, you can say input to the turbine, mechanical power input to the turbine is varied, then it will actually affect the speed. So the question is, if forget about the mechanical power for the time being, how would the electrical quantities be affected? Okay, the mechanical power is affected, that's fine, because they are interlinked. Now, if this rotation is varied, if it is a conventional machine, we generally represent the speed by the synchronous speed. So, and that is written by, expressed by 120 F over P, okay? So this is the synchronous speed, and let's say this is the speed. So as long as this is synchronous, then the frequency, this Fe would be constant, okay? So let's say if it is a 2-pole machine, or let's say 4-pole machine, you expect 50 hertz. So how much is it? It is around 1500 RPM. So let's say if it is an individual machine, it's not coupled to the infinite bus. Let's say we talk about an individual machine. Okay. So if somehow this speed is varied, this is the fixed number of poles available in the machine, so it's not going to vary. So this quantity is going to be affected. Okay, if it is a, let's say if it is a machine which is running in individual manner. And at the same time, because these will be varied, this real power would be affected. Real power would be affected. So to control this PE, and as you said, to control the PM, one of you said that this PM would be affected, and PM and PE are closely coupled. They will try to keep balance following the swing equation to make the system stable. So, so variation in the omega actually would be translated as variation in frequency and control in real power. On the other hand, variation in your excitation voltage, VDC, is going to affect the variation, is going to affect the terminal voltage as well as the reactive power output. So this is in short the summary. So that means the frequency here is actually being governed by the speed over here as well as the number of poles over here. But of course, if we can make this, of course, this, if this P is kept constant, then of course this FE is directly coupled to the speed, shaft speed over here. So change in shaft speed will actually affect your output voltage frequency, okay, as well as the output power, active power from the generator. The steady state speed, how do you get the steady state speed of the synchronous machine? You have to know the speed of the prime mover that drives the shaft, okay? So that means the speed at which this rotor is moving at steady speed, at a steady state, is of course related to the speed of this shaft. Okay. So the speed at which the shaft would move, if and only if we can ignore some of the mechanical associated rotational losses, then we can say, well, this speed would be the same, exactly same as the speed over here. Or if you allow some mechanical or rotational losses, then of course there will be some small deviation from this shaft speed to this rotor speed. So, and ultimately the prime mover output, that is the turbine output, it would affect the input mechanical torque to the synchronous machine. And there are some examples of the typical prime movers. Of course, you may see the diesel engine, application of diesel engine or gas engine, or the gas turbine and the steam turbine or the hydro turbine. And these are mostly conventional examples. Okay. So now that means if we want to have some control over the speed or control over the mechanical input to the generator, okay, the mechanical input to the generator. So where is the mechanical input actually residing? Let's see. So if this is your turbine block, this is the shaft, this is your generator, and this is the generator output. Let's say this is the same shaft that is being coupled. So this is the input energy to the turbine or input power to the turbine, whatever we say. And this is actually the mechanical power, PM. So the output of the turbine is actually working as the input to the generator. It's the same. And here you have the electrical output power. So in a sense, if we want to vary this to supply the required demand, okay, of course this P is varying. It will ultimately go to the load, rotational load or stationary load, okay, DC load and AC load, any kinds of electrical loads. So this load is actually constantly varying, going up and down, up and down. And accordingly, the demand at the generator is varying. That means PE is varying. And to cater for this variation in electrical output, this PM has to be varied. So that means this control over here is actually a prerequisite for a successful operation of a power system. So if you don't have any control over PM, that means we can't actually control PE from this side. Okay, we can't control it. And that means if we are not able to control it, the real power output That means if the load is varying, let's say if the load is getting reduced, P remaining constant, so then PE for a reduced amount of load, you have to incur some losses. On the other hand, if PE again is constant, you are not controlling it from the input side, then if the load goes on the other way around, that means if goes in the positive side, there is a positive change in the load, then with this PE, you are actually unable to supply the demand. So that means in that case, what you have to do, you have to go for some load shedding. You have to go for some reduction in the load. So thus you have to incorporate some sort of control mechanism at the turbine so that you can have some control of PM, and that would actually that is only possible by controlling the input energy to the turbine. So if it is a hydro turbine, that means what we are going to control actually, we are going to control the water flow rate. Okay, water flow rate to the turbine. So that would be our control variable. We are going to control it, and controlled variable is PM. So now let us see a schematic of conventional hydro turbine power plant. There are two diagrams. At the top, you have a bigger picture. At the bottom, I have given another picture, the smaller version with some additional components. So let's go through the components. There are basically 5 major components. First of all is the storage reservoir. And this is the reservoir. The job is to basically give us some sort of head, water head, or in short, we call it height, H. So what is the need of this water head? Basically, it will give us some sort of potential energy, where M is the mass of the water, G is the gravitation, and H is the height. So that means if we can raise this water level, we are going to have some increased amount of potential energy, hydro potential energy. And vice versa. And the flow of water from these reservoir to the turbine. This is the location of the turbine. Okay, turbine blades are shown actually there. And the water that comes from the reservoir, there are actually 2 parts until it flows or until it reaches the turbine blades. The first part is known as the intake valve or intake tunnel. So this is the intake tunnel, this part. Or you can also look at this diagram, this part. The first part is known as the intake tunnel. Allows the flow of water to go through it to the turbine blades. And the next part is known as the penstock with a larger slope. Okay, so the tunnel slope is, the intake tunnel slope is pretty small. However, the penstock slope is very high, as is seen from the diagram. And then you have the sluice gates. So this is one control mechanism implemented here, so that this channel is actually controlled. So if this sluice gate is completely closed, then there is no water going to get into the tunnel through the penstock up to the turbine, because the channel is closed. So the movement of the sluice gate is basically in the vertical direction. In this direction, it opens, and in this direction, it closes. And this is the maximum possible opening for the sluice gate. Okay, the maximum possible opening of the sluice gate is basically defined by this distance. Okay. So there is a control, how much water you are going to allow from the reservoir to the intake tunnel through the penstock up to the turbine. And then you have the turbine blades. And once you are allowing the water to flow through the intake, because of the slope and because of this gravity, actually there is a velocity of the water. So if you simply close the sluice gate completely, you are not going to get any kinetic energy, any motion of this water. Okay, it will be stagnant. On the other hand, if you slowly open this, then due to the gravity, this stored kinetic energy over here, or the stored potential energy over here, mgh, would be converted into some sort of flowing energy. That is the kinetic energy. So you can call it as half mv squared. And again, this is the mass of the water that is flowing, and this is the velocity of the water that is flowing through the penstock to the turbine blades. And this half mv square is the input energy to the turbine blades. And once this hits the turbine blades, you are going to get some rotational energy. So there is actually, you see different stages of energy conversion taking place. So this is potential energy, this is kinetic energy. Then at the output of the turbine, it is rotational energy or mechanical energy. This rotational energy transfers the energy to the turbine through this shaft. So this is the shaft. And once it is being transferred, then the generator shaft rotates, and generator converts this rotational or mechanical energy into electrical energy. So these are the energy conversion steps. And then of course, you have the three-phase cable, three-phase transformer for stepping up the voltage. And then you have the high voltage transmission line, and power is being supplied to the transmission network. And the water, after being used up by the turbine, it goes to the lower part of the river. Okay, and that flows away. So this is basically known as the tail water. That is the tailing part of the whole system. And this is the head part, or the starting part of the whole system. So then you have the hydro turbine. So this is actually the hydro turbine. So there is another component. Of course, there is dam. If you don't have the dam, actually, you are not going to get the water reservation, reservoir available here. So the dam is being built artificially so that you can have this water head available, so that it can withstand the water pressure against the wall. Okay. So this is the dam. And the last element, or the last component that is left, is the surge tank, which is not actually shown in this diagram, but I have taken another diagram for showing the surge tank. So you see the location of the surge tank. And of course, another thing which is not shown here is this turbine gate valve, which is the second control mechanism available. So the turbine gate valve actually allows or controls the flow of water from the penstock to the turbine blades. So you see the turbine gate valve, this is the second control mechanism. So this is the control gate valve. Again, if you fully open it, that means you are allowing maximum possible of water, maximum amount of water. If it is fully closed, that means you are actually allowing no water to be flowing from the penstock to the turbine blades. And that means a minimum power would be generated, or no power would be generated from the generator, because there would be no rotational energy available at the turbine blades. So in a sense, we will call it, let's say, the opening and closing of this control gate valve. Of course, that terms would appear later on also, but let's denote it by the capital letter G. So if G is 0, that means your gate is completely closed. If G is 1, that means your gate is completely opened. And this G value, the opening and closing of the gate valve, actually controls that how much power would be transferred and would be converted from the rotational energy to the, from the kinetic energy to the rotational energy. Because if you are closing it completely, then although there are some water available, but ultimately they would become stagnant, okay, after a certain amount of time, because the channel is closed, the water cannot flow. So there is no velocity available at the water for the water. So there is no kinetic energy. The velocity would become 0 at the penstock water element, and then you are not going to get any motion available in the water. So of course, there is no question of any energy getting converted from kinetic energy to the rotational energy, and of course to the electrical energy. So thus you are actually implementing a control with the help of the positioning of the gate valve over here. Very critical position. Now what will happen? Actually, why would we like to close or open this gate again? As I said earlier, if you have more demand, PE, more demand increases, or we can say P load, this is the demand increasing. So you have to supply this demand, of course, from the generator, that is P electrical should be increased. So P mechanical should be increased. So gate valve should be opened so that more water can flow and more kinetic energy is available. As simple as that. And vice versa, okay? So if the case is reversed, then P load would be decreased, PE would be decreased. You need less mechanical input at the turbine. So gate valve needs to be closed. So if that is the case, once you are closing the gate valve, you remember the water is actually flowing, okay, flowing in here. So if you are suddenly closing the gate valve, then what will happen? This water that is available in the penstock, it will get a back pressure. And that back pressure would cause, if this channel was not there, let's say this channel is closed, there is no surge tank, there is no such tank there. So if this channel is closed, what would happen? Due to this back pressure, the valve is closing, okay, suddenly the water can go forward, so it will get a back pressure in this direction, reverse direction. And due to that, there would be huge pressure being created on the walls of the penstock, on the tunnel, as well as on the gate valves of the turbine itself. So thus, to reduce the pressure, this is also known as water hammering in short, okay, as if you are hammering the walls of the penstocks with the help of the water. It is known as the water hammering. So to get rid of the water hammering and to increase the life of your structure, whatever structure you have built, you will allow that additional water, okay, the pressure that is being exerted by this closing of the gate valve. So whatever water is there, due to this back pressure, if you can allow some water to go through this path, then your pressure would be reduced, okay? So the water that is actually getting stuck here due to the closing of the gate valve, now it can pass through here and it could be stored here for further usage. Once what is the another benefit? Once you are again closing the valve, again opening the valve, then now this amount of water that was stored in the surge tank, it can travel quickly. Okay, you see the water from the reservoir, it has to travel a larger distance, this distance, then it will flow through the penstock. But if you have the surge tank, besides helping or saving from the water hammering concept or water hammering problem, the surge tank actually gives you a water surge, okay, sudden water surge, which has to cover a smaller distance. Only it has to cover the penstock length. It doesn't have to cover the tunnel length. So this is another benefit. If you have a sudden increase in load, you are quickly opening the gate valves and you are allowing this water and this water to flow together. This water will take, of course, less time to reach the turbine gate. So this is the other benefit. So these are actually the components or the principal or major components associated with the hydro turbine plant. And this is the very simple explanation actually for the operation or the basic operation of the hydro turbine system. Okay, so now we would like to model whatever is going on and whatever was discussed till now. We would like to model it mathematically. So let's see. There are several models as we discussed earlier for other parts or other components of the power system. Like as we started, if you remember, we started with some nonlinear model for the synchronous machine. So similarly here, there could be nonlinear model for the hydro turbine. But remember, we are using most, all of the equations or all of the dynamic models that we have achieved are in the linearized form, okay, or incremental form. So our target is to again take this probably nonlinear model. We start from the nonlinear modeling and then we will switch to the linearized model. What is the benefit of the nonlinear model? It is precise. Okay, it is precise. It can capture the nonlinear phenomena. And it is actually, but it is not used, actually not used in the power system small disturbance stability or small disturbance modeling. But it is precise. So this is the benefit, but this is the problem. Because we are focusing on a small disturbance modeling, so the nonlinear model is not going to be of any use for our purpose, but it is precise. It can capture even the nonlinearities. The linearized model, on the other hand, it is some approximated model. If you remember, as we did for the synchronous generator, we resorted to Taylor series expansion and some truncation of higher order terms. So that truncation actually made the model approximated. It was approximate model. So of course, this is approximated model. So there was truncation of higher order terms. So due to this truncation, the model became approximate, and thus it is only valid. This model is only valid for a certain operating point or a steady state operating point and around that point, in the neighborhood of that point. And of course, because it is approximate, it should not be used for any phenomena that needs the study of a large disturbance analysis. Okay. So for large disturbance analysis, we are not going to use the linearized model. For the small disturbance analysis, we are not going to use the nonlinear model. Okay. Because in our course till now, we are only focusing our studies on the small disturbance model. So we will continue with the linearized model or the approximated model. Now, which of the variables are of our interest? The variables of interest are basically PM, as we said, okay, in our model, and that appeared in the second state equation, that is the speed dynamics of the synchronous machine. So del PM minus del PE. So this is our target. This is our variable of interest now. So you would like to model this. Okay. And of course, most models, if it is a steam turbine or gas turbine or any diesel engine, all those models, actually you expect from those models is this value, is this variable, okay? Nothing else. You want the dynamics of del PM, be it diesel engine or gasoline engine or whatever. Your only target is to get some dynamics for this d del PM with respect to time, of course, d del PM over dt. But in this course, we are covering the hydro turbine modeling. So the working principle of hydro turbine has already been discussed in short, of course. And let's see what is next. Okay, so this is actually what I have already mentioned. Okay, the power initially is available in the form of potential energy, and that energy depends on the water head. And depending on the opening of the sluice gate, you have a variation in the water availability of water, or availability in the amount of water that will actually flow through the intake tunnel and then to the penstock. And once it starts to move, that means the water starts to move, you have the kinetic energy. If the sluice gate is closed, you only have the energy in the form of potential energy available in the reservoir. Then what is penstock? It is mentioned, is basically nothing but a channel. The gate valve, it is a control valve, and the location we have already shown in the diagram. The gate valve position, of course, if you vary the gate valve position, then you are actually varying the amount of power PM. And of course, that would be translated as the rotational motion of the turbine blades. And the turbine converts the available kinetic energy into mechanical energy that runs the alternator shaft. So this part is actually covered. Now let's start the modeling on the mathematical part. So let's say we have some water height available from the gate to the water level in the reservoir. So that means, what is the gate or the gate valve? So you see, this is the turbine gate. So that means somewhere here. And by the term H or effective H, this could be treated as H, or let's say some arbitrary H1, which is not of our interest. Our interest is this H. Okay, this height, because actually this height is actually creating the amount of flow, because this is the H and this is the gate valve position. So we are interested in this H. This is the H effective, or in short, we will call simply it as H. So once we define H, U, it is the water velocity. That means the water speed that is flowing through the inlet tunnel, or flowing from the reservoir through the inlet tunnel, through the penstock up to the turbine blades. G is the gate position, as I mentioned earlier. So G can have a maximum value of 1, that means fully open, and minimum value of 0 means the gate is fully closed. So these are the three symbols that we have introduced for the modeling, H, U, and G. Now the velocity of the water, how do you represent it? Of course, the velocity of water is related to the kinetic energy available in the water, and let's say that is half mv squared, because we are using U. So let's make it U. Okay, half mu squared. This is the kinetic energy of the water, and that is only available from, this is H now, from the stored potential energy in the reservoir. And if we neglect any, let's say, friction loss along the way, so you can equate both of them. Then what you can do, you can cancel out m, and remember this is the gravitational acceleration G. Okay, and this is U squared is twice GH. So that means U is proportional to, you can write square root of H. Okay, because 2 and G, these are constants. So we have taken it into some constant, a proportionality constant, and then H would be left. So U is simply a square root of H, proportional to a square root of H. So let's say this is the first relation that is required to establish this relation over here. We have U proportional to square root of H. So this relation is covered. Remember that we have some proportionality sign. The next is pretty simple and straightforward, U and G. That means if you are opening G more, what would happen? So that means if you're opening this turbine gate valve more and more, what would happen to the water? You are actually allowing more water to flow. Okay, of course, considering you have sufficient reservoir. So that is an assumption, unvalid assumption. So we will assume that we have sufficient amount of water available in the storage or in the reservoir. So when we open the gate valve, of course, we are allowing more water. That means there will be more velocity of the water. Okay, water would be flowing at a higher speed. So simply it is modeled as proportional, as a proportional factor, but with the help of a proportional factor. So the second relation is U is proportional to the gate valve position. You open the gate valve, you get more velocity. You close the gate valve, you get less velocity. Okay, you completely close the gate valve, of course, after a certain transient, the U would be 0. Okay, water would become stagnant. So if we combine these two, then simply you can write U is equals to some proportionality constant Ku G square root of H. So this is how we are getting it. Okay, the velocity of the water. Now for a small change in the water velocity, what you do, you take the incremental model. Why we are taking the incremental model? Again, as we said, that all of our dynamic equations or the dynamic models or the simulation or done till up to this point are in small disturbance domain. So we will also now do what we will actually take the incremental model for U, the velocity of the water. So then what you need to do, you need to simply calculate these partial derivatives. Why partial? Because it is a variable of it is a function of two variables, G and H. So what you have to do, simply you take del U is di U by di H into del H plus di U by di G into del G. Pretty straightforward. For a steady state operating point, what we can write, that means for a certain operating point where the operation is steady, there is no dynamics, we are simply using the notation 0, subscript 0. So simply this is used, and this has been used as U0 equals K, the U, this is a proportionality constant, G is 0, that means the value of gate valve position when U is equals to U0 and H is equals to H0. So this is how it is written. So now you have to calculate di U by di H and di U by di G. And these, of course, are to be evaluated. One thing is missing, you can add it for the completion of the expression. These are to be evaluated at H equals to H0 and G0, or more generally, it should be H0, G0 and G0, H0. That means whatever expression you get after taking the partial derivative, if there are any appearances of H and G, it should be equated to H0 and G0 respectively for both of these two cases. Okay. So this is what it means. So now let's continue with the derivation. So we have del U, and del U is 1 upon 2 H naught square root K U G naught del H. So let's see how it comes. So what we are trying is getting the di U by di H. So what is U? U is simply KU G square root of H. So if you want to take di U over di H, what would be the result? So this is KU and G, because remember, you are only taking the derivative with respect to H. So H has a square root. So simply it is take the derivative H to the power minus half. Okay. So that means, and now you have to evaluate it. Okay, let's complete the equation first. So G half 1 by H. So this is the di U by di H. Now what you have to do, you have to evaluate it at H naught and G naught, the operating point. So you take it half KU, G equals to G naught and H equals to H naught. So this is how it comes. And then this is the part multiplied by del H, because you have the del H here. So this is this. Okay. And then again, you calculate di U by di G. So you have again U, write down the U expression. And now you are looking for di U by di G. KU is a constant. Now H is another constant. G, simply it would be 1. And then you have to evaluate it at H equals to H naught. So simply put 1 H naught. So this is what you have. And then multiplied by del G. So this is the del G. So this is how you get it. So once you have got the expression for del U, so now remember, all these are still in their actual variable. Okay, actual variable. We haven't per unitized, or we haven't scaled it. We haven't done anything. These are some actual quantities. Means this velocity is in, let's say, meters per second. Meter per second. This H is in meters. By actual units, I mean these things. Okay, H is in meters, U is in meters per second, and so on. Of course, gate position is simply some numeric value. Okay, fraction of 1, where 1 means between 0 and 1. Any value between 0 and 1. Some real valued parameter. Okay, so then let's continue. So what we will do next? We would try to have a normalized version for the expression of the velocity. Normalized version means nothing but to represent this, this whole expression in a scaled version. Okay, nothing but in a scaled version. So how do you scale it? You scale it with respect to the operating point. So what's the benefit? The benefit is that if you are scaling it for a with respect to a generalized operating point, you see in the operating point, we had the variables in the operating point. What we had u equals u naught, g equals to g naught, and h equals to h naught. So this was the configuration of the operating point. So now if you normalize your expression of del u, then what you achieve actually, now this model, the normalized version becomes valid for any operating point, okay? Because it is in normalized version. It is for any combination of u0, h0, and g0. So it becomes a scaled version. So this is the benefit. So you don't have to deal with large numeric values, okay? You can say also in that manner. So the small disturbance model becomes del u bar, where this bar means all, you see now the presence of all these over bars. So these over bars are nothing but representation or representation of all these variables in terms of the normalized version. So how to achieve this? You see del u by u naught del h over twice h naught plus del g over g naught. Why are we normalizing in this fashion? Because as I said, this is the actual representation or actual expression. So when we are normalizing it, what we are doing simply, we are dividing the whole thing, dividing the whole expression by u naught on both sides. Okay, so let's divide it by u naught on both sides. So what do you get? What is u naught? You have the u naught here available. So it is, let's keep it as u naught. Then you divide these by u naught. So ku g naught is square root of h naught. Also here ku g naught square root of h naught. Cancel ku on both numerator and denominator wherever possible. You cancel out g naughts, you cancel out h naughts. So what's left? So the left here on the left hand side, we will call it del u bar, the whole thing. On the right hand side, the first part is this. So you see h naught under square root, there are 2. So it will become h naught. In the numerator, on the first part, on the right hand side, you have del h plus del g over g naught. So this is the expression, and this is what we are saying as half del h bar plus del g bar. Okay, so this is the derivation, simple steps. So this is how we get it. So you see, this is del u over u naught. So this part is actually done here. So del u bar is half h del h by h naught plus del g by g naught, and then we are making it like half of del h bar plus del g bar. So this expression is done. So this is the small disturbance model in the normalized quantities. So now if we continue further, what we get, remember our target is to achieve some expression for PM. Okay, we haven't seen the presence of PM till now. So now at this point we bring PM, okay, into our derivation. So what is PM? PM is the turbine mechanical power. And again, the turbine mechanical power is expressed as some proportional term for the water head, some proportional term for the velocity. If we combine them, simply you get some proportionality constant h and u. So this is the turbine mechanical power. And remember, it is the turbine output power. So simply, if you have any confusion with this, just look at any basic on turbine output power. I think you should be able to get the idea. How is it coming as Kp, which of course Kp is a proportionality constant, but what is H? H means intuitively how we can explain it. If we increase the H water head, of course, you are going to get much more mgh. Okay, if water head increases, that is converted to half mv squared, which is kinetic. This is potential energy. This is kinetic energy. And then you get the rotational energy. Okay, from the half mv squared, you get the rotational energy, that is PM. So you see PM has a link with H. So you can establish this in some way. At the same time, you can establish the link in this way. If velocity increases, PM should also increase. Okay. So in this manner, you can also intuitively you can establish this relation, but of course there are background physics for this derivation, but that is beyond the scope of our course. We are not going to go into that detail. Simply the expression is required and intuitively we can explain it. So that's enough. And again, for the steady operating point, what we have, again, PM naught, simply you get H naught and U naught. So this is for any steady state operating point where we had U naught, H naught and G naught. So at the same operating point, now we are saying that our mechanical input from that, or the mechanical input to the generator, or the output from the turbine, is PM naught. The small disturbance model for this is pretty simple. So in the same manner, we can go for the small disturbance model for the PM. So we have KP, H, and U. If you need del PM, what you would do, you would say KP and di PM. So it would be del P, and so what you have to do, di PM over di H into del H plus di PM over di U into del U. So this is the part that are required to be calculated. So di PM over di H, what it would be? Simply, if you take the partial derivative of this, you see there is a presence of only H, so it would be 1. Di PM over di U, again, you take the partial derivative of this with respect to U, you see there is only 1. So you see this is the expression. So del PM is actually del H plus del U. So this is the 1. And then you take the normalized version. So what you would do, you would simply take del PM over PM0 equals del H over PM0 plus del U over PM0. Now there are nothing to be cancelled actually. Okay, you see there is no coefficients over there with del H and del U. So you can simply write del PM over PM0 is del PM bar equals del H bar plus del U bar. Okay. So once that is done, so you have the small disturbance model for del PM in terms of del H and del U and in the normalized version. Now, if you want to express the same del PM, now this del PM in the first part, it is expressed as an addition of the normalized del H and the normalized del U. If you want to express this del PM, instead of del U, if you want to incorporate del G, so simply you can use this expression over here. And that means del U would be replaced. So you can write from here del H plus del U is half del H plus del G. So it is 0.5 del H plus del G. So that means it is 1.5 del H plus del G. So this is what we have got. Okay, so but still there is no dynamics. Okay, we have got some we have got the presence of del PM in our derivation. We have introduced del PM, but remember we are looking for some dynamic model for del PM. So in the next slide, we will be starting the dynamic part of the model, and it would not take long to actually complete the modeling part. So let's have some patience until we are done with the modeling part for the turbine. So now let's look into some dynamics associated with this flow of water, because we are saying the water is flowing. Okay, so as we are saying the water is flowing and there is gate valve, so and depending on the positioning of the gate valve, the velocity is affected. So once we say the velocity is affected, means there is some sort of acceleration. And once you have acceleration, you can introduce some sort of, or not some sort of, you can introduce or you can take help of the Newton's second law or Newton's law of motion. And in short, that says F equals m into acceleration, where m is the mass on a body and a is the mass of the body, a is the acceleration of the body, and F is the force applied on the body. But again, if as we are interested in some sort of incremental representation, so we can write it, m is a mass is not going to be actually changed. So a, we call it, let's say, del A. So we are looking for this. Okay. So now, so what is actually m? How do you represent m? M is the mass, and we can represent it by rho, which is the mass density of water, into V, the volume of the water. Okay, so the volume of the water and the mass density of the water, if you multiply these two, you get m, the mass of the water. So that means we can replace this by this. Now, what is the volume of the water? How do you calculate the volume of the water? Let's say this is the pipe or this is the tunnel. This is the water flowing. Okay. So this is the length of the pipe, L, and this is the cross section of the pipe. This is the cross section through which the water can flow. So this is A, this is the cross sectional area. So that means the volume, this volume, let's say if it is a cylinder, simply this volume can be expressed as L into A. And this is what you are seeing there. And then what is acceleration? Simply acceleration is d, what is your velocity? U over dt. So you see, we have already got the left hand side of the expression done. And that is coming in this manner. So this is actually this part. That is done. So the part that is left is basically related to the force. And how do you relate force with whatever is whatever are appearing here? So let's see. Again, we have to take some help of some basic physics. So F and pressure, okay, force and pressure, what's the relation? We know the other one, pressure is force per unit area. Okay, and again, this is cross-sectional area. So force is pressure, water pressure into the area through cross-sectional area through which the water is flowing. Now we keep A, the cross-sectional area, because A is there, and we have to think about the remaining three terms. And this is the pressure, because we are looking for incremental. Okay, let's make it incremental form. So del F, remember we are looking for del F. So del F is the cross-sectional area, because the pipe area is not going to be changed, the cross-section of the pipe. The pressure is going to be changed. And then this can be written as, okay, first let us write what is pressure, water height, density, gravity, H rho G. Okay, so now which one of these could change actually among these three? Because we are looking for del P. So del P, of course, the density, water mass density is not going to be changed. It is a constant. G, the gravitational.
H.
Yeah, so it is H. So we should write del P equals, sorry, yeah, del P equals rho G del H. So you introduce rho G del H, and this G is nothing but actually AG here, this AG. So we have got it. So del F is replaced by A del P, and del P is replaced by rho G del H, because water head height could be affected based on the operation of the turbine system. gate valve positioning, etc. And this G is actually this AG. Okay, what is AG? Acceleration due to gravity. So this is the G I am talking about. So this G and this AG are same. So thus we have established a relation between the velocity variation or the dynamic in the velocity of the water that is flowing through the pipe and the force being applied on the water. Okay, force available on the water of mass m. So now, of course, we have established the relation, but you see there is a small negative sign over there. Can anyone explain the reason? Okay, I have written it just for my convenience. Okay, so this is the reason actually. Now, if you look, okay, what are the variables there? On the left hand side, the variable is actually change in velocity. Remember, change in velocity. It is not only the velocity. It is the change in velocity. By change, we always expect some positivity. Okay, when we say d by dt of some variable, we expect that it should return me some positive things. Okay, so when it becomes negative, then we say, then we have to incorporate some negative sign. So now let's see how this negative sign is actually associated with this expression on both sides. So what are the variables? The variable on the left hand side is the change in velocity, water velocity through the pipe or through the tunnel, whatever. And on the right hand side, we have change in water head. And the remaining things are constant. So we don't have to bother about these things over here. We only have to bother for thinking about the presence of minus m. We have to think about this d del u by dt on the left hand side and del h on the right hand side. Now, let's say this is the pipe. This is the water head. This is the dam, reservoir. This is the sluice gate, etc., etc. So water is actually flowing here. So this is the velocity of the water that we are talking about. Okay. Once the sluice gate is opened, even by a little amount, the water will get, of course, some velocity. What is del H? Remember, del H, there is a turbine blade. We talked about some turbine blades. And this was the H head. Okay. In which direction H increases? Top or bottom?
Top.
H increases in this direction. Excellent. Now, if we are, okay, when will the velocity of the water increase? When we are opening the sluice gate, right?
H is going down. Then.
Yeah. So when we expect increase in the velocity of the water head must go down. So this is the reason why there is a negative sign, nothing else. Okay. So in short, if you expect positive change in velocity, it implies, or it is only possible when you are allowing some reduction in the water head H, otherwise not. So they have a negative relation between themselves. Okay, is it clear?
Yes, sir.
Okay. So now let's continue. So the difficult part is done. Then it's pretty simple. The remaining part, these are the explanation of the symbols. L is the length of the pipe or the conduit or the penstock, as I mentioned. A is the cross-sectional area. Rho is the mass density. And of course, all of them has their own units. It's still, this is in actual units. So L could be in meters. A could be in meter squared. Rho in mass density, whatever is the unit of the mass density, probably kilogram per meter cube, because it is density. Ag is the acceleration, meter per second is something like that. So these are actual units. Okay, I haven't mentioned the units, but then we are normalizing it. So for normalization, we divide by this peculiar part. Okay, A, rho, Ag, H naught, U naught, simply for normalization, nothing else. And simply for allowing us to bring this concept of TW. Okay, nothing else. So how do we introduce this TW? On both sides of this Newton's law, we simply divide both sides by this A, rho, Ag, H naught, U naught. A, rho, and Ag, these are nothing but constants. H naught and U naught, these are point specific, operating point related. Okay, these are not constants. Okay, not always constants, but for a certain operating point, these are constants. But These A, rho, and AG, these are always constants. Okay, water mass density is constant. Of course, yeah, again, the cross-sectional area, once you build the penstock, this A is constant and AG is always constant. So rho and AG, these two are always constants. Once your hydroturbine generation system is being built, A become constant. H naught and U naught, once you are fixing a certain operating point, then these also becomes constant. Okay, so in a sense, all these are constant when all these conditions are satisfied. That means your penstock is being built, you have fixed a certain operating point, so all of these becomes constant, and you divide on both sides by this multiplication, big multiplication term, multiplicative term. So what you are left with, let us see. So you divide rho LA d del U by dt. It's minus A rho AG del H. Okay, you have to divide by this thing. Okay, A rho AG H naught U naught. A rho AG H naught U naught. So these things are cancelled. A rho AG. This side A, sorry, rho A, these are only cancelled. And you are left with some AG. Okay, so let us see. So you have L at the top, and what you have? AG at the bottom, H naught at the bottom. You have one del U here. Okay, so let's take this del U because we are looking for some normalized expression, and this U naught being a constant, we can divide it over here. We can take it within the derivative term, okay, because it is a constant for a certain operating point. On this side, what we have minus del H by H naught. This is the H naught, and U naught, we can bring it here. This U naught, okay, we can bring it here. So now you see it is same. L U naught over AG H naught, and there's normalized means del U by U naught. Del H normalized means minus del H by H naught. So your job is done. Okay, we have reached here. That is done. So once that is done, then this part, we actually take the unit as TW, which is nothing but defined as water time constant. Water time constant means like any other transient system or dynamic system, whatever is the concept, background concept of time constant, the same concept applies here. It is another time constant, but for a hydropower system. Okay, that means if you open the gate valve, how much time will it take to raise the water level? Okay. If you close the gate valve, how much time it would take to reduce the water level? Okay. All same concept. Okay. Same concept of time constant applies, but for the water flow, because now the dynamics is being modeled for the water. So for the water flow dynamics, this is the equivalent concept of time constant represented by TW. The unit should be in second. Remember, the unit should be in second because it is a time constant. You can check, always cross check whether this gives you back a unit of seconds or not. So let's check. L is the length, so this is meter. U naught, it is the velocity, so it is meter per second squared, divided by AG. What is AG? AG, oh sorry, velocity is meter per second. Sorry, there's a mistake. Velocity is meter per second. Then you have AG, it is meter per second squared. Inverse, H naught, it is meter. So you cancel out M, S, 1S, so you have S. So you see, you are getting second. So it is, yeah, it is validated. That is the unit of TW is second. We can call it some kind of water constant associated with the hydroturbine water velocity dynamics. Okay, so once that is done, then the remaining part is, I don't think it's anything special. So now it is in time domain. We have introduced the dynamic equation in time domain. This is the equation of our interest, but again, this is in del U, the velocity. We expected something in terms of del PM normalized. Okay, so let's see how we can do that. Okay, before going there, what we have to do before reaching the expression of del PM, simply we have to take the Laplace transform to make it convenient, just to represent it in terms of transfer function model. So in Laplace domain, simply what you will have, this d del u over dt, this would become s, d by dt, this would become s, simple s, the Laplace operator, multiplied by del u equals to minus del h. So all the variables now you see in the form of del s. Okay, the form of del s. So do you see this is del s, this is del s, d by dt has become s. So this is the simplification in Laplace domain. Now we already have a relation del h between, okay, we have a relation between del h, del u and del g. Which relation we are talking about? If you go back. Okay, so you see we have a relation between the normalized relation actually. Yeah, this relation. So from here what we get, you see there is a relation between del h. So half del h equals del u minus del g. So that means del h equals 2 del u minus del g. So this is the relation that we are talking about here. So using that relation, what we do, we simply replace del h here. We simply replace del h with this equation. So there won't be any del h. Okay, there won't be any del h left, of course, in this equation. So we replace this del h by this, and after simple rearrangement, we get this equation. Now we only have del u here and del g, and the time constant tw, and the Laplace operator s. Again, we have another relation, del pm is 3 del u minus 2 del g. Again, this is some expression that we got here. Okay, so del pm is 1.5 del h plus del g, and of course you can relate del h. Here it is del h and del u, here it is del h and del g. You can also do it other way around, like del g and del u. Okay, all the same. So pm could be expressed, can be expressed, of course, as a function of del u and del g. It is always possible. So what we did here, actually, we replaced del u. Then for getting this, what we have to do, we have to simply replace del h. So then you will get del u and del g. And that expression is actually this expression. Okay, it's very simple. So you get the expression. Where it is? You get the expression here, and then you eliminate del u. Because why? Because we need del pm, d del pm by dt. We need that expression. We want that expression. So we are replacing all the presence of del u from here, and simply del u is replaced by so del u can be replaced in the form of del pm and del g, with the help of del pm and del g, and then you will get that, you will see that there won't be any del u. Instead of that, you will have del pm related to del g. So this is what we will get. After eliminating del u, you will get del pm and del g related with this transfer function. So this transfer function block tells us that you have got another transfer function block for representing the hydroturbine dynamics, where the input is del g normalized, output is del pm normalized, and in between you have this. So you see, now it is becoming very straightforward, looks good. You change the gate position, you get some variation in the mechanical output from the turbine. Okay, so this is the transfer function, simple transfer function, first order transfer function. So that was our target. Okay, in time domain, if we take this in time domain, simply you have to cross multiply this with this, and multiply this with whatever we have here in the numerator. And if we take S as d by dt, then you simply get this. So this is our expression. I talked about dpm by dt. Of course, it is in del pm because it is in incremental form. Then we have some time constant, and here we have d del g by dt. Okay, in the right hand side we have some d del g del pm by dt, del J, and something else. Of course, we have another TW, and of course, we have some other parameters. Okay, so this is our desired state equation with a problem. Can you identify what is the problem in this expression? Why we have to dig more for further simplification of this? Why we shouldn't be satisfied only with this expression? Anyone? What is the problem with this expression? Okay, first of all, what are these? What is the state variable in this equation?
PM. Del.
Okay, why not del G?
Yeah, del G also.
Okay, so this is the problem. You see, we have a single equation, but we have two time derivatives available. So we can say either this is the dynamics for del PM, or we can also say this is the dynamics for del G. So this is the problem. Keep it in mind. For eradicating this problem, what we would do, remember this control, this is a control valve, okay, control gate valve. For eliminating this, what we have to do in the next lecture, we will introduce governor. Okay, and we will see that this differential part can be expressed with the help of some algebraic expression. So if we can do that, then we can erase this second time derivative in the same single expression, and then we are done. Okay, so this is why we have to next look into the dynamics of the governor. This will come from the dynamics of the governor. We don't want two time derivatives appearing in the single ODE. That is a problem. We have to remove any one of these. So in the next class, inshallah, we will see how we take help of the governor model and we get rid of this. Okay, so that inshallah we will take in the next class. But before we finish, I know I'm over time by a little bit, but let me allow few, maybe 2-3 minutes. I'm done almost. So this is probably the last slide. Okay, so in terms of actual variable, means it is in the incremental form, del PM, del G everywhere. In the incremental form, sorry, in the actual variables, but it's still normalized. It becomes PM bar over bar. Over bar means normalized. PM simply means it is the nonlinear variable, or normal actual variable. It is not in incremental form. This becomes PM, this becomes G, and this becomes G. Okay, there is no del G and del PM. So this is the definition of those, that PM is nothing but PM naught at a certain operating point plus the deviation del PM. G is nothing but G naught plus some deviation. For power unitization, what we have to do? For power unitization, remember this is the power expression, mechanical power input to the generator. So if you look for power unitized expression, you have to divide by base power. And actually for a generation system, base power is always in base MVA. So you divide both sides by base MVA, what you get? When you divide by the base MVA, your PM converts into TM. Remember in per unit, power and torque are equivalent. Power and torque are equivalent. So you don't write PM, you simply write it as TM. TW is still a time constant, so you don't have to bother about that. 2 is there, PM becomes TM, G now becomes G per unit, and again here G becomes G per unit. So this is in per unit normalized expression or dynamic expression for the turbine torque, okay, or equivalently turbine output power, generator input power, all the same. Okay, so we have, what we have done today is we have looked into some basic building blocks of hydro turbine power plant. Then we have got through the operation, of course, in a simplified manner. We have gone through the steps associated for the hydro turbine dynamic modeling. And again, remember, this is a pretty simplified model. Okay, that is suitable for our course. We have only taken very simplified model. Okay, for hydrothermal dynamics representation. And then finally we have got it, but still we have some issues, because we have got two differential variables in the form of PM and G. And as we said, we have to eradicate one of those. And in the next lecture, we will see how we are going to start actually to eradicate this dg by dt, and we are going to replace this by some equivalent algebraic expressions, and that would come from the governor model in the next class, inshallah. Okay, any question?
You know, model, why we are using hydro turbine and not any other prime mover, for example, diesel engine?
No, actually it depends on your availability of resource. If you have the structure available, if you have the water resource available, then you can build the dam if you have the money, of course. If you have the structure that allows you to build some dam to get the reservoir part done, to get the penstock and tunnel part done, then you go for hydro turbine. Okay, you don't have water resource available, you have diesel or the oil available, petroleum available. Okay, you can get diesel with a reduced cost, go for diesel. You get the idea? It depends on your fuel availability. Okay, wherever you have whichever fuel is available to you, you go for it. Was this your
model will be changed or it will be same?
no, model would be probably a little different, because the derivation part would be different. Okay, because in the diesel part you don't have any head, you don't have the velocity of water. Okay, probably you have to go with the flow of your diesel. Okay, you have to go in the dynamic for the diesel engine. In that case, the prime mover is the diesel engine. So if you study the diesel engine dynamics, then and only then you will get the idea of the diesel or the gasoline gas turbine parts. Okay, for the steam, again, it's a little different. It is not exactly same. So the model would actually vary a little from one to the other. But ultimately, you should expect some kind of expression in this form. This will remain fixed. This will be varying. This will be varying. Okay, these things will not remain the same. Get the idea?
Yes, sir.
But of course, this is not, I mean, if I start talking about all those, then probably I cannot touch the remaining part of the course topics. So there is the problem. So this is just to give you a hint how we are going to model and how we are let's say any hydro turbine. And with this concept, probably it would be easier for you in the later part of your career if you want to continue with these topics later in your PhD maybe, or maybe in your future research area or job area. If you require some modeling sort of things, probably hydro turbine is done more or less, but steam turbine is not done, gas turbine is not done. Okay, but if I go for all the detailed modeling of all the turbines, then probably we will be going away from the course contents a little bit. So that's why I'm not touching everything. Okay, I'm not touching everything, just giving you some ideas. But of course, that modeling would be different. It would not be exactly the same, but this part would remain same. Okay, you will be looking for some sort of change in mechanical power input to the generator, and this would come from the whatever mechanism is working in the diesel. If it is a diesel engine, then you have to go for the whatever mechanics is inside, physics is working inside the diesel engine. Probably you have to look into that and you should get it. Okay. Okay, any other question? Already we are in the overtime zone, so probably you don't have any question. Okay, so then we should conclude the session, and inshallah we meet in the next class on Monday. Assalamu alaikum.